Now let's talk about the effect of salinity on the solubility of a chemical. As salinity increases, the solubility of neutral organic compounds tends to decrease. Why is this? Well, you may or may not have learned in your aquatic chemistry class that ions, like say for example our friend iron 2, they tend to be solvated, right? They've got water molecules surrounding them helping to dissipate that positive charge, right? And how many do they have? Well, frequently they have 6. They have 6 water molecules. I'll just draw them as circles here. 6 water molecules that are surrounding the iron and helping to dissipate that +2 charge over a wider area. Well, those 6 water molecules are no longer available to solvate your compound. They're busy, they're tied up. And so as a result, there's just less water available, and so the solubility of the compound is going to have to go down. And there's a guy named Seshanow who figured this out, and he actually came up with an equation to describe this effect. And of course, because your textbook really loves dealing in terms of activity coefficients, the equation here is written in the form of activity coefficients. But remember, since the activity coefficient is proportional to 1 over the solubility, we could write this equation in terms of solubility, and we just have to have a negative sign over here. Okay, but for now, we're going to keep it the way it is because Renee Schwarzenbach loves his activity coefficients. So the activity coefficient of the compound, your compound I in water in the presence of salt, is equal to its activity coefficient of your compound I in regular old water with no salt, times 10 to the Ks, which is this Seshanow constant, times the molar salt concentration. And you might remember from the beginning of this solubility lecture that I talked about the fact that seawater, typical seawater out in the middle of the ocean, has a salt concentration of about 0.5 molar. In Raritan Bay, where it's kind of mesohaline, you might have a solubility, a salinity of around 0.3. And in freshwater, it's pretty close to 0. So obviously, if salinity is 0 here, then 10 to the 0 is 1, and there's no change in the activity coefficient. So we need to know what the Ks is, and we need to know what the molar salt concentration is. There's kind of problem with this equation in the fact that they use salt here in molar units, molar salt concentrations. And, you know, this is an artifact of the thing that Seshanow was a chemist, right? He was not an environmental chemist, and he was certainly not an oceanographer. Because if I was an oceanographer, I would not express salinity in terms of molar units. No one in oceanography does that. Oceanographers would use things like practical salinity units, or they might talk about salt concentration in parts per thousand. And converting PSU, practical salinity units, or parts per thousand, to molar concentration is not trivial because the density of the water is changing. So if you're looking for me to give you a simple equation to convert PSU to molar salinity, I can't do that. Believe me, I once had to do this, and I had to have an entire spreadsheet to try to convert these numbers back and forth. So just be aware of that. These PSU units and other units that oceanographers would use are not going to work in this equation. But the point is also that the difference here, and we're going to do some calculations and we'll see that this is true, the change in the activity coefficient is usually not huge. So the difference between 0.51 molar and 0.49 molar salt concentration is trivial. So, you know, oceanographers get very excited about tiny differences in salinity. They're not going to matter for this equation. All right, so it turns out that the Seshanow constant of a compound in seawater is basically a weighted average of its Seshanow constants with all the salts that are in the seawater, multiplied by the mole fraction concentration of those salts. Now, because we're environmental people, we don't really spend too much time thinking about the solubility of a compound in water that has some weird salt like cesium chloride dissolved in it, right? We don't care about that. That's not important to us. Really, what we care about is seawater. So it turns out that seawater, you could calculate a Seshanow constant for seawater by doing a weighted average of all the other Seshanow constants for all these other salts, but no one actually does that. What they really do is just go measure a Seshanow constant in seawater. So here's a table 5.6. So this is salting constants, Seshanow constants for benzene, naphthalene, and 1-naphthol. So of course benzene and naphthalene are pretty much totally nonpolar. benzene is smaller, and naphthalene is about twice the size of benzene. Naphthol is almost the same size as naphthalene, but it's got an alcohol group on it. So you have two pretty much nonpolar chemicals and one relatively polar and hydrogen bonding chemical in this table. And somebody has taken the trouble to go measure Sessionow constants, Ks, for these compounds in a whole bunch of different salts. Sodium chloride, magnesium chloride, sodium sulfate, all kinds of crazy things, even these amine salts. This is a quaternary methylamine chloride, and this is a quaternary methylamine bromide. So they've taken the time to measure the Sessionow constants for these chemicals and all these different salt solutions. And you notice, and by the way, here's the mole fraction concentrations of these salts in seawater, and you can see that by far the most important one is sodium chloride, then there's a little bit of magnesium chloride, and then the rest of the stuff is pretty unimportant in terms of how its effect on the solubility of chemicals anyway. And so you notice, okay, here for benzene and sodium chloride, the Ks is about 0.2. For naphthalene, about 0.2. And for 1-naphthol, about 0.2. So for most of these chemicals in sodium chloride, which is the main component of seawater, the Sessionow constant is about 0.2. In other salts, it could be quite different. So here we have sodium sulfate, and it's got a Sessionow constant for naphthalene of 0.72. So now it's much, much bigger. 4 times, almost 4 times as big, 3 or 4 times. And the reason for this, of course, is that when you dissolve sodium sulfate, you get 3 ions. You get 2 sodiums and a sulfate. And so, of course, it's, because it's more ions, it's going to tie up more of those water molecules and give you a higher Sessionow constant. But for a lot of these other salts, we're still around 0.2 or 0.3 for the Sessionow constants. So it doesn't matter too much. It matters some what the salt is, but as long as we're sticking with sodium chloride and seawater, you're talking about Sessionow constants of around 0.2. This table is giving you some Sessionow constants for a whole bunch of different chemicals in seawater now, right? So now we're in seawater, which is a mixture of many different salts, but mostly sodium chloride. And again, you notice 0.2, 0.3, 0.2, 0.25, 0.21, 0.24. They're all around 0.2, 0.3. Pentane, hexane, butanol, pentanol. Now, when you get to these longer chain aldehydes, now you're getting some pretty serious Sessionow constants. But you go down back to some more normal compounds. Here's dimethyl sulfide, butanone. Again, it's around 0.2. PCB is around 0.3. Benzene, toluene, ethylbenzene, all of these organic compounds around 0.2 or 0.3. Phenols, a little bit lower, 0.13 to 0.17, but still not too far off. So what this suggests is that if you don't know the Sessionow constant for your chemical, which, let's face it, you probably don't, you can look at this table and you can make a guesstimate. If it's an aldehyde, you might want to go over here and guesstimate a higher number. But if it's just kind of your run-of-the-mill organic chemical, you'd be doing pretty well if you estimate a Sessionow constant of somewhere between 0.2 and 0.3. That's going to get you close enough and do a pretty good job of helping you describe the influence of salt on the solubility of a chemical.